Hi there, Science 9. So there's been a fair amount of new stuff this week in terms of I gave you a lesson and a project, but the project's not due for a while. And you're definitely overdue for a lab that I've been excited for a while about introducing you to. That's the Flame Test Lab. I gave it the title, How to Make Fireworks Step 1. The reason for that is because you're going to see how to give a color to a flame. You can buy kits in like Canadian Tire, that kind of thing, around summertime that have substances that you can add to a flame that will give the flame a color. What you're doing then is you're buying metal salts, ionic compounds, that when you put them into the fire, you get colors. The same kind of technology or application of chemistry is used in fireworks and making pyrotechnics, and you're going to look at some of that today, but also I want to make a bit of a connection with chemistry, so let's get going. So first of all, purpose is this. We're going to compare the flame colors, or also I sometimes say flare colors, and solution colors of 8 different metal ions. You're going to see what those are in a moment. I'd like you also to look at this. This is a little bit like a Bohr diagram. As you see, you have a nucleus in the middle, and then there's a number of shells, a little bit like a cross-section of a gobstopper or something like that. That is a conceptual diagram of an atom with electron shells, except I'm not labeling any electrons in there. I'm not trying to make a Bohr diagram here, but I do want to show you something. So if you put an atom of a substance in an environment that's really hot, like the middle of a flame, you're adding a lot of what's called thermal energy to that atom. It ends up going very fast. Its electrons also get very excited. What can happen when the electrons get excited is this. Imagine a situation where we have an electron that's, say, right here. In that shell, that would be the third shell out. We add an immense amount of thermal energy, like taking a sample of that and putting it into the middle of a flame. What can then happen to that electron is that thermal energy can bump it up to shells that are otherwise not occupied. These are electron shells that don't normally have electrons in them, but because the electron's so excited, so much energy's been added to it, it goes up there anyways. So let's say it hops up to this far shell over here. It's not going to stay there for very long. Almost the moment it gets put up there, it will follow its natural tendency, its attraction, back towards the nucleus, because electrons, being negative, are attracted towards the positive nucleus. So it gets bumped up by the thermal energy, but then it's going to drop back down. When it does that, it's going to release that energy that it absorbed. But it releases it in a very special way. It releases it as a tiny flash of light. Now, you may be aware that there is this thing called electromagnetic radiation. It's got radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and cosmic rays. A wide range of different forms of what is really all just light, some of it visible and some of it not. Now, different units of that light have different amounts of energy. X-rays give you cancer because they got lots of energy. Radio waves have very low energy. Now, what's happening here with that electron jumping down is for any pair of orbitals of shells that's going from down one to the other, there is an exact amount of energy that's released. And because it's released as an exact amount in a tiny flash from each atom, that exact amount of energy, get this, it corresponds to a certain color of light. The colors of light depend on the what's called the wavelength. The amount of energy that's in there depends on wavelength. And so what you will see, if it's visible light, is you'll see a flash of light that is emitted as it goes down from one shell to another. It emits a certain amount of energy, and we know it's that certain amount of energy because the light takes a certain color. Now, of course, if just one atom does this, you won't see it because the atoms are so small and the amount of energy released per atom is very small. But if you take a little chunk of it, a little crystal, and put it into a flame as well, this is happening to trillions of atoms, or at least billions of trillions of atoms simultaneously. When that is happening, the number of those tiny flashes, all of the same wavelength of light, all of the same color, really adds up. And so as a result, you get a visible flash of color. Now, where does that figure in when it comes to what we're going to do today? I'm going to show you flame tests for several ionic substances of metals. I chose this because I changed the design a little bit of what's expected in the textbook, but I added some stuff to it. One is I want to see you compare the flame test result with the result of making a solution out of it. Making a solution, you're just taking some of the salt, the ionic compound, and you're adding water, mixing it around. Some solutions have a color, some don't. You're going to compare the solution color with the flame test color, and you may get the same result. We may get the same result, or we may not. So that's the one purpose. The other purpose is I want us to look for evidence that it's the metal. Because ionic compounds are made of a positive ion and a negative ion. I've told you that already. The positive ions are metals, and then the negative ions are nonmetals, or combinations of nonmetals. Now, you might think to yourself, well, could it just be the nonmetal part that's responsible for the color of the flame? Maybe. We're going to look at that. We're going to look at that because I'm going to look at 2 salts of each of these ionic compounds. Not just 1, but 2. So I've got 8 metals, 2 salts of each. You're actually going to have 16 results for this. And each of those results is going to have it's going to have its own a solution test and a flare test, or flame test. So let's get going here. I want to get us into the results. Now, you should, with this, be having the document open, the flame test lab. The data entry for this is on the 2nd page. Just a second. Yeah, the 2nd page starts with the color of the flare, if any, with just the glass rod and so forth. So yeah, it is page 2. You'll be filling in the results. I'm going to get the Bunsen burner going, and we'll get this started, and I'm going to explain what I'll be doing for each of these samples.